Okay, so we're in 12.5 now, and I want to say this is probably the biggest section, has the most content in it of all the sections in chapter 12. This is where we're starting to develop some equations for important important objects that we deal with a lot in this class, lines and planes in particular. So it turns out that the vector concept that we've been working on the past three sections is really helpful when trying to determine the equation of a line or a plane in 3 space. You already know how to find the equation of a line in 2 dimensions. You've been doing that since Algebra 1. And we've also seen the equation of a couple of planes, but those are very special planes. We saw, for example, something like z equals 5 is the equation of a plane. But that's a plane that's parallel to the xy plane, and those are kind of the easiest cases. But we want to be able to find the equation of any line in 3 space, as well as any plane in 3 space. So again, beginning with lines, the minimum information that we need in order to find the equation of a line is 2 things. We need to know one point on that line, which I'm going to call P naught. Its coordinates for this purpose will be x naught, y naught, z naught. And then we also need some vector that's parallel to that line. So here's my line, I'm calling it L, and here's that point that we just know is on the line. We'll be given this information typically. And then here's a vector, it's drawn as a position vector, but it's specifically supposed to be parallel to the line L. So V is parallel to L. Okay, with just that information, we can come up with our equation for a line. And in fact, we're going to have 3 different forms that we use for the equation of a line, which we'll develop all on this page. So notice from this picture, if I want to come up with the equation for any curve or any plane or anything like that, I have to think about what an arbitrary point on that object looks like. P naught is a specific point that we're given, but I'm going to choose some arbitrary point. I'm going to call it P and give it coordinates x, y, z. This point can be any point on this line, and I want to see how all these things relate to each other. So from this diagram, if you look at where P naught and P are, if I were to form a vector that has P naught as its initial point and P as its terminal point, I can see that that vector would lie completely on the line. That would make it also parallel to this vector V. Now, in this diagram, this vector is called A. This comes straight out of your book. But we can find that vector explicitly because, again, if you notice how it relates to these 2 vectors here and here, R naught, which is what I'm calling the position vector for P naught, and R, which is what I'm calling the position vector for P, A is actually just the difference between these 2 vectors. Back in 12.2, we showed that if we did R minus R naught in this case, the result would be this vector A right here. Okay, so R minus R naught is a better name for this vector, and that vector, as per our previous discussion, is parallel to the vector V, which means that these 2 things are scalar multiples of each other. So if so that means there exists some scalar, let's call it T, such that R minus R naught is equal to T times V, scalar times vector right here. Now, if I were to add the R naught to both sides, then what I have here is an equation for a line called a vector equation. And remember, R is the position vector for that arbitrary point, x, y, z. And so we think of this as kind of like a variable here. R naught is fixed. It's a constant. It's a unique position vector for that known point. And V is also fixed or constant. It's that one vector that's parallel to our line. T is allowed to vary here. So T is kind of like the variable in this vector equation. And for that reason, we oftentimes see this written not just with an R there, but R of T. It's fairly common to see this written as an R of T instead of just an R because this is a function of that scalar T. How does the scalar T affect this point on the line? Well, again, if you think about where T came from, it's that scalar that we're multiplying V by to give us this vector R minus R naught. So it basically is going to control the size of this vector, which moves this point P along the line while P naught remains fixed. If T is given a negative value, this vector will flip over and give us points over here. So we can kind of see how that position vector r will end up tracing out the entire line as we let t take on all real numbers. Okay, now that vector equation, even though it's a useful technique, or it's useful or it's helpful when deriving, I should say, the equation of a line, typically we don't use the vector equation in a lot of the work that we do in this section. Most of the time when we're trying to come up with equations for a line, we use the other two types that we're about to talk about. So those can be derived from this. Remember, r was the position vector for the point x, y, z. r naught was the position vector for the point x naught, y naught, z naught. And v, that vector that we were discussing before, even though I didn't mention it, it's right here. It has a, b, c as its component form. And because these 2 points are terminal points of position vectors, then those coordinates would also be the components of those position vectors. So what all this is leading to is I'm going to rewrite the 3 vectors in this equation, r, r naught, and v, all in terms of their component forms. That would look like this: x, y, z equals x naught, y naught, z naught plus that scalar t times abc. If I were to multiply that scalar in here and then add these 2 vectors together so that I get a single vector on this right-hand side, this is what that would look like. Okay. Now the fact that this is an equation literally means that x is equal to x naught plus ta, and y is equal to y naught plus tb, and z is equal to z naught plus tc. So if I extract those as 3 equations, which I have written right here, those make up what we call the parametric equations for the line L. Now, tie this back to what we would normally be given about a line when trying to come up with an equation. X naught, y naught, and z naught all correspond to the coordinates of some known point on that line. A, b, and c are the components of the vector that happens to be parallel to that line. So again, all we need is a point on the line and a vector that's parallel to the line. T is a variable, right? It's not specifically set equal to anything. Oh, I see a little mistake here. I should say z equals. I put it on this side, but yeah, z equals z naught plus tc. Now, in each one of these equations, if you notice the t showing up here, if I isolated the t in each one of these 3 expressions are what t would have been set equal to: x minus x naught over a, y minus y naught over b, z minus z naught over c. And because all of those are equal to t, we can say that they're all equal to each other. And this set of equations right here is what we call the symmetric equations for that line L. So 3 different equations that we've talked about, all describing the same line but just given in a different form. The vector equation shown here, parametric equations shown here. Don't forget that z equals this. I forgot to type that out. Symmetric equations shown here. Okay? And again, look in the symmetric equations. X naught, y naught, z naught, those are the coordinates of the point on the line. The denominators here, a, b, and c, all come from the components of that vector that's parallel to that line. Oftentimes that vector v that's parallel to the line, we call that a direction vector. So you may hear me use that term here and there. Here's a simple example using this. A line L passes through the point 4, negative 1, 5, and it's parallel to this vector 2, 1, 4. We want both parametric and symmetric equations for this line. This is very straightforward. There's no real work to do. Remember, the parametric equations are x equals x naught, where x naught is the x coordinate of a point on the line. 4 is what we have for that. Plus t times a, where a is the x component of our direction vector, this guy. I can write that as plus 2t. Y and z in our parametric equations is found similarly. So y would be negative 1 plus 1t, or just plus t. And z would equal 5 plus 4t. And those are the parametric equations. Notice there's no real work to do as long as you know which values go where in these equations. The symmetric equations are just as easy. So remember, the symmetric equations are x minus x naught, which in this case is 4, over a, which is 2, and then that's equal to y minus y naught, which in this case looks like y plus 1, over b. In this case, that's a 1, and I know that putting this over 1 doesn't change anything, so I can leave that alone. And then I set that equal to z minus the z naught, which is 5, and put that over 4. So these are your parametric equations. These are your symmetric equations. And if we were doing a problem where we were given these equations and we wanted to extract information out of them, notice that I could either use the 4, negative 1, 5 here, or the 4, negative 1, 5 here, thinking in opposites. These are minuses here. I could extract a point from the line, and I could also use the denominators here or the coefficients on the t's here to extract the direction vector from that information. Okay? Here's a slightly harder problem. So by harder, I mean more interesting. It's not as straightforward. This time what we want to do is find parametric equations for a line L that's passing through the points 1, 3, negative 2, 2, 1, 9. Okay, and then we're asked a follow-up question. At what point does this line intersect the YZ plane? Okay, so in order to do this, remember what it is you need. Always tell yourself, in order to come up with the equation of a line, any type of equation, any of those three forms, you need to have two things. You have to have a point on the line, and fortunately we have two to choose from here, and you need to have a vector that's parallel to that line. Well, the example here doesn't tell us a vector that's parallel to the line, but we have enough information to find one. Because both of these points lie on the line, the vector that uses this one as an initial point and this one as a terminal point, or vice versa, it doesn't matter, would lie completely on that line. Or in other words, it would be parallel to that line. So I can define my direction vector by the vector that has this as an initial point and that as a terminal point. I just subtract components. 2 minus 1 is 1. 1 minus 3 is negative 2, and then 9 minus negative 2 is 11. Okay, easy enough. So now what do I need to do? Well, I need to come up with parametric equations for the line described here. That means I need to use my direction vector, and I need to use one of these 2 points. Let's use the first one. Those parametric equations would be x equals 1 plus, the 1 comes from right here, plus 1t, or just plus t, like that. Y is equal to 3 minus 2t. 3 minus 2t. Then z is equal to, where's my point? Negative 2 minus 11, or I'm sorry, plus 11t. Right? Make sure I subtracted all that in the right order. Yeah. Okay, so now what? Well, the next thing we're asked to do, let me circle these because that's part of our solution. That's something that we were looking for. The next thing I need to do is find at which point does this line intersect the YZ plane. Well, remember, if you are looking at 3 space, x, y, z, remember the YZ plane is the one that contains the y and z axes. And if we have a point in the YZ plane, like this, then that would make its x coordinate 0. 0, y, z, whatever y and z happen to be. So this indicates that I'm looking for where x is equal to 0. Because then if this line passes through that point, we're talking about the specific value, or talking about the specific point on the line where x is equal to 0. So using my parametric equations, let me set x equal to 0. 0 equals 1 plus t, which implies t equals negative 1. So when our parameter, for these parametric equations, when our parameter t equals negative 1, this line will be passing through the YZ plane. I can plug that value of my parameter into the other 2 equations to find what my y and z coordinates are. So y equals 3 minus 2 times negative 1, which we have right there. That would equal 5. Z equals negative 2 plus 11 times negative 1. That's negative 13. So that means, remember, it passes through the xy plane where x is equal to 0. So we have a 0 there. 5, negative 13. That would have to be the point at which that line intersects the YZ plane. All right, more to that problem than the previous one. It's more of an interesting problem. Okay, now in some applications we don't want the entire line. Sometimes all we're looking for is a line segment joining a couple of endpoints. And so let's suppose that we're doing just that. Let's suppose that we want a line segment joining these 2 points right here. And let's suppose that the first point has a position vector of r naught. And let's suppose the second point has a position vector of r1. Okay? And we're looking for an equation for just that line segment right there. You can see that. I know I wrote that really small, it's hard to read, but that hopefully that gives you the idea. Well, notice again, r naught and r1 are position vectors, and the difference between those position vectors, r1 minus r naught, for example, would be this vector right here, which would be parallel to the line. So r1 minus r naught is a vector that's parallel to the line. That means if we wanted to look at the vector equation for that line segment, I could swap the v out for r1 minus r naught because it fills that role. It's a direction vector. Now, if I were to set up my equation this way and distribute the t in, then collect like terms, you should see this pop out. 1 minus t times r naught plus t times r1. R equals this expression. That is the equation for a line segment that takes us from the point with position vector r naught to the point with position vector r1, as long as we put a restriction on t. Notice if I plug a 0 in for t, this term goes away. This term becomes 1 times r naught, or just r naught. So when our parameter equals 0, we're at this first endpoint, the one with the position vector of r naught. If t equals 1, then 1 minus 1 is 0. This term goes away, and I have 1 times r1. So by the time t gets from 0 to 1, I've now reached my other endpoint. So that creates a restriction. We let t be restricted to the intervals 0 to 1, and that will trace out just that line segment instead of an entire line. Okay? All right. Next example. So this one involves a term that we need to define. You should have learned this term in geometry, but that may have been a long time ago, so it's worth mentioning. In 3 space, pairs of lines can be categorized in 3 different ways. 2 lines will either be parallel, and remember parallel means that 2 lines are non-intersecting, but contained in the same plane, okay? So this is like a pair of parallel lines. They can be intersecting, so these 2 points intersect at a line. Or there's a third possibility, something called skew. Now, 2 lines are called skew if neither of these are true. If the 2 lines are not parallel nor intersecting. What does that look like, though? It's difficult to draw this, but it's easiest if you have a couple of parallel planes that you put the lines in to see it. Suppose one of these lines looks like this, and the other line looks like this, for example. Because these 2 lines are in parallel planes, and the planes will never intersect each other. Therefore, the lines will never intersect each other. But they don't look parallel. One appears to be going a different direction than the other. This is what we call skew. Okay? Now, how do you show, given these 2 lines that we have parametric equations for, L1 and L2, how do you show which of these 3 categories these lines fall under? Well, if these 2 lines are intersecting, then I should be able to find a point of intersection. And in that case, I would pursue that, and that would actually lead to a system of equations that I try to solve, and yada, yada, yada. If the 2 lines are parallel, then that would mean that their direction vectors are also parallel. It turns out that that's actually much easier to verify. So that's usually where you want to start. Check and see if they're parallel. If you've ruled these two out, if you can show that the two lines are not parallel by showing that their direction vectors are not parallel, and if you can show that they're not intersecting by show that there is no point that the two lines have in common, then by default you've shown that they're skew. So showing that two lines are skew is done indirectly. You rule out these other two cases, and then you say, if these are not true, then this one must be true. But it's easiest to start by checking if these two lines are parallel. So for L1, let's suppose that we have a direction vector for L1. How do you get the direction vector for L1 from its parametric equations? Well, remember, those components come from the coefficients on the t, so negative on the t's. Negative 12, 9, negative 3. Okay? That's the direction vector for L1. What's a direction vector I could find for L2? 8. Looking at the, these are using S's because they don't want it to be confused with the parameter used up here. But the coefficients are still what we're using. 8, negative 6, and then 2. Okay? Now, if these two lines are parallel, then these two direction vectors should also be parallel. But how do you check to see if two vectors are parallel to each other? Well, the key is to see if one is a scalar multiple of the other. And comparing these numbers, you start to suspect that maybe they are related that way. But to be sure, what we can do is compare the components using quotients. Negative 12 divided by 8 is negative 3 halves. 9 divided by negative 6 is negative 3 halves. And negative 3 divided by 2 is, again, negative 3 halves. That suggests what the scalar is that's being multiplied to this second vector to get this one. And you can, in fact, verify that pretty easily. V1 is equal to negative 3 halves times V2. So that tells me that the two direction vectors are parallel to each other. One might be pointing like this, maybe the other one's pointing like that, but the two lines are definitely parallel because of that. Okay? There you go. I think there's an equation in your book that shows that they're in either intersecting or skew. You should know how to do that as well. I'd recommend going and checking that example out. All right. This feels like a good point to stop this video because we're moving on to planes now. So we'll go ahead and finish up the rest of this in the next video.